And we're on, and I don't have a magic pen. There we go. Hello, magic pen, yes. All right, so this is section 8.6, and I moved the due date to 8.6 till either today or tomorrow. And 8.7 I moved to Thursday. So I've got number, which did I say, 5. Says take the integral from negative pi over 2 to pi over 2 of 15 times the cosine of t over parentheses 2 plus the sine of t, and that whole denominator is squared. And on this one right here, they actually gave us a bunch of information, but I'm going to skip that. They give us a table of values of t to use and the corresponding y values, but we're just going to build this from scratch. So some things to consider for this interval. I'm trying to get from negative pi over 2 to pi over 2. 0 is right in the middle, and we want n to be 8. And remember, n has to be even if we're going to use Simpsons Rule, because we're pairing up intervals to put a parabola through them. And the beautiful thing about Simpsons Rule is we don't have to actually calculate those parabolas. It just turns out to be a weighted average of the y values. It's subintervals inside, yeah. So in this case, I want to cut those in half and in half again. And so there's my 8, make believe they're uniform subintervals. So let's see, this one would be a negative pi over 4. This one would be negative, pi over 8. And that would be 1, 2, 3 pi over 8 over here. Other side, pi over 4 is in the middle. Pi over 8's in the middle there. And then 1 pi over 8, 2 pi over 8, 3 pi over 8 would be over here. So those are my subintervals right there. And let's see, we are asked to set up the trapezoidal rule for this. So remember, the trapezoidal rule for the area is the sum as n, let's use k, goes from 1 to 8 in this case, of h over 2 times, and let's see, we have to finish off at yk, so this must be y sub k minus 1. So that's the trapezoidal rule right there. And so the fun part is we have to calculate each of those y values, which is one reason the online homework gives you the table of values, so you could just kind of plug them in. So I'm going to try and do it just a slightly different way. In order to figure out those y values, I need to come up with a sequence for these x values here. And so we did similar things way back when we were playing with right-hand endpoints. So to figure out what the kth x value is, I make a note that I'm starting at negative pi over 2. And the width of these intervals, these subintervals, is always the width of the whole interval. So that's pi over 2 minus negative pi over 2 divided by how many intervals you want, right? That's what we call delta x, or often in this chapter, we've been calling it h. So cleaning that up a little bit, that's basically pi over 2 plus pi over 2, which is pi. And kind of like we see here, all these guys are pi over 8 apart. So that's my h, or delta x. So all I have to do is start on the left endpoint and then add on multiples of pi over 8 to jump through these guys here. And we did the same thing way back in chapter 5. So if k is 0, I'm exactly at negative pi over 2. If k equals 1, I have pi over 2 minus pi over 8, which would be 4 pi, negative pi over 2 plus pi over 8, which would be 4 pi over 8 negative plus pi over 8, which gives me what? Negative 3 pi over 8. And so we'll keep adding pi over 8 as we jump through this. All right, so is everyone with me how this is going to generate the x values of my interval right up here? All right, so those are the x values that I have to plug into my function here and here, which gets pretty messy. Okay, so the book again gave the table of numbers to say, hey, these are the y values. So a couple ways I could do it. I could whip out a spreadsheet to do that, or I could use something like GeoGebra or Wolfram Alpha. So I think just for fun, I'm going to generate that spreadsheet that they have in the homework, so you can see how to build your own. I'm going to use Google Drive. Oops. Switch to the right folder. If you use Google Drive, it's always a good idea to put yourself in the folder you want something to live before you make a new file, so that you don't have to move it later. All right, so I'm going to make a spreadsheet for homework 8, 6, 5. And I'm going to calculate the x values and the y values here. So what do we got? We have the x values are starting at negative pi, and can I just, yeah, it wants parentheses for pi, divided by 2. And then I just want to take that above number and add to it pi over 8. And so I'm just generating a little function that's going to get the numbers I want. So we should see that's going to take me from, come on. Oh, did I do the wrong button? Try that. There we go. And I got to go one more. Okay, so here's my pi over 2, 3 pi over 8, pi over 4, pi over 8, 0, and then I get the positive versions. Then to get the y values, I just type in my function. So equals 15 times the cosine. And notice it says, hey, it's got to be in radians. Okay, it doesn't do degrees by default like most calculating machines. And my x value is just that guy right there. And then divide by parentheses 2 plus the sine of t. Close the sign, close the denominator, and square the denominator, and fill down. And so this is the table that the online homework provided for you. Interesting, they actually claimed the last one was 0.00001. Let's see, is that true? What's cosine of pi over 2 is 0. Yeah, that's pretty cut and dry. It's not 0.00001, it's actually 0. Anyway, and we could then actually use, let's see, can we program the spreadsheet to do the trapezoidal rule? I wasn't going to do that directly. Oh yeah, I can, pretty easily. Anybody remember what the trapezoidal rule does to these y values here when we list that out? It doubles the inner y values, because they all have, the inner y values all are part of, so this x value right here is part of the trapezoid on that side and that side. So anyone in the middle gets used twice. Yeah, so I can actually have the spreadsheet help me do this. So I could then say double each of these guys in the middle. So I just make a note to myself, this is 2 times y in middle. Always good to label what you're doing. Those are 0. I'll include them anyway. And then what do I want to do with these guys here? Just add them up, right? Now, so then I want the sum. So I'll make a note, I'm doing a sum here. So equals sum. Oops. There we go. Now that's not quite the answer yet, because we have to multiply by h over 2. So then I want to take h over 2 times the sum. So I'm just making a note of that. Oops, I didn't mean that to be all caps. And so I want to take the number above times, let's see, what did we decide h was? Pi over 8? Oh, So h is pi over 8, and then I have to divide that by 2. And so the sum here should be about 9.78, according to the trapezoidal rule. So next we'll check the error on that, which is going to be very exciting. So if I were going to plug this into something like, what's that? No. If I was going to plug this into something like Wolfram Alpha or GeoGebra, something that does sums for me, then I would have to take these x values right here and plug them into my function here and here in my sum. That gets a wee bit messier, and these are the x values I'm plugging in, where I get a k directly, and then k will have to be a k minus 1 in that one. So to enter this in some other kind of program that does sums for me, it would look something like this: sum, or maybe we have the Riemann sum. We still have to have our h, pi over 8 over 2. And then we would have the sine, is that, no, we start off with cosine, sorry. 15 times the cosine of our x values, and all our x values look like this. Negative pi over 2 plus whatever k is. The first time through, it's actually a k minus 1. So I'll have parentheses k minus 1 times pi over 8, my h value. And that's divided by, did I close my parentheses? Yep. Parentheses 2 plus the sine, and I didn't leave myself enough room here. Let's move it and condense it a little, times the sine of the same set of x values, negative pi over 2 plus k, oops, times pi over 8. And let's see, close the sine, close the denominator, and square it. So this is where it gets messy in terms of a Riemann sum, because then I've got to add on the next y value. So all of this right here, oh, that should be a k minus 1. I was right the first time, k minus 1. This all right here is just y sub k minus 1, okay? So this is why they gave you the table. Otherwise, you have to type all this stuff in, which is pretty nasty. So I'm still in this parenthesis right here, and then I'm adding on the next one, which would be 15 times the cosine of my x values, which are negative pi over 2 plus some multiple. This time it's the kth multiple of pi over 8, divided by parentheses 2 plus the sine of that same x value, plus the kth multiple of pi over 8. Close the sine, close the denominator, and square it. And now I can finish closing that parenthesis right there. And all that has to be from k equals 1 to 8. So that's the Riemann sum version versus the spreadsheet version. The spreadsheet, yeah. So we could even use the spreadsheet for Simpsons Rule. So I'll show you how to do that next. So again, I could type all of this into Wolfram Alpha. I could type it into GeoGebra. Either one will do it fine, provided I put all my parentheses in the right spot. Now, I've done a fair amount of these just for fun, and I almost always miss one of those parentheses. And Wolfram Alpha will guess for me. It'll say, hey, you have a parenthesis out of place. This is where we think it goes. This is weird. As good as it is, it always guesses wrong. It puts it, no, that's not where I want it. And then eventually I put it in the right spot. So being really careful with parentheses is important. One thing I got into the habit of doing when I'm working with programs like GeoGebra or Wolfram Alpha, if I start a parentheses, I close it at the same time, and then I arrow back in the middle. That way I'm always within the right parenthesis. Okay. Sometimes for complicated expressions, it does get a little trickier, but again, we could type that in. I'm not going to, because it'll take a while. And Samantha looks bored. So we're going to make it more exciting. Let's take a look at Simpsons Rule, and then we'll look at the errors. So Simpsons Rule, I gave a couple of different versions of the other day. And again, the beautiful thing about Simpsons Rule is although we use parabolas to get the top of the area sections, we don't actually have to calculate those parabolas. They just come out for us. And so with Simpsons Rule, we need to add up a bunch of y values, and they're grouped as follows. It's always y0 plus 4y1 plus y2. Then we pick up again where y2 on the edge of y2. So I need a different color. Let's go with red. So then picking up with y2, it'll be plus 4y3 plus y4. And then we grab the next pair, which starts off with y4 plus 4y5 plus y6. And it just keeps repeating this pattern over and over and over again until you get to the end. When you condense that, and then just again, another vision of why that works, this is x0 there, this would be x1. This would be x2 here, this would be x3, right? x4, oops, x4, and I think that's far enough for now. In order to put a parabola through here, I need 3 points. So those guys get grouped together. I should have made them blue. So maybe those are the y values for that section right there. And Simpsons Rule essentially finds that parabola right there. But we have to pick up again for the next grouping at y2. So starting here, we group the next two together. And we find that parabola, whatever it looks like there, and so on. So every third one, or every other one, sorry, gets used twice. The middle ones get weighted 4 times. Okay, so condensing my formula, I get the first y value only gets used once. The second one gets used 4 times, at least has a weight of 4. The next one gets used twice, so it's a 2y2. And then the next one's in the middle, so it's a 4y3. So we go 1, 4, 2, 4, 2, and it keeps oscillating between 4 and 2. And so if we kept going here, we would have plus 4y5. So if there were only 6 intervals, we would be done. Let's see, y5. If there were more, like 8, which is what we're about to do, then let's slide this over so I can fit it. We're going to have plus a couple of more. I'll have 2y6 plus 4y7. And then finally, y8 is at the end. It only gets used once. So the pattern is the first and last get used once. Otherwise, it starts with a 4 and then goes 2, 4, 2, 4, ends with a 4, and then finally a 1. So we always get that pattern. And so we can use a spreadsheet to pull that off. Then there's the Riemann Sum version, which is a little bit wacky, but we'll take a look at it. For the Riemann Sum version, you have to use a counter that's half of what n is. So I called that k the other day. I called it j on my notes. So as j goes from 1 to n over 2, guaranteeing we have n was an even number, it's going to be whatever h over 3 is. And then you're going to have 3 different y values. The one in the middle gets used 4 times. If we look at the pattern here, let's see, back. The one in the middle is always an odd number that gets 4 times. Okay? The one on the end is always a power, is always an even number, 2, 4, 6, and so on. So what that ends up being is this would be a 2j at the end. And think about it, if I go to n over 2, what's 2 times n over 2? It'd be n, right? So that takes me right to the end. This one has to be 1 less than that. So this right here is 2j minus 1. Now remember, we needed an odd number in the middle. So 2 times some integer guarantees an even number. 2j minus 1 guarantees an odd number. And then this one's going to be 1 less than that, so that one's 2j minus 2. So if you were dying to set up a Riemann sum, this is the way you have to do it if you're going to use Simpsons Rule. It's a wee bit trickier than, so imagine writing that up for our current function, right? Think about how bad it was for the just the trapezoidal rule. For Simpsons Rule, we need one more of these packages, okay? So, little bit trickier. We're going to do it with a spreadsheet. So back to my function over here in my spreadsheet. Where'd it go? There it is. So in the book for this problem, they give you this table of values. So I'm going to pick up with those again and make a new sheet. Call this sheet Simpson. I'll share this sheet with anybody if they want it. Okay. So with Simpsons Rule, the first one gets used once, so I can just say, okay, just use whatever number is there. How many times does the next one get used? 4 times, so I go equals 4 times that number. How much is the third one used? Twice, so I just go equals 2 times. Once I establish that pattern of the first two, I can just highlight the two of them and fill that down. And if I double click this one, it should say, yeah, you're being used 4 times. So it automatically picks up the pattern. Again, in order for that to happen, I had to get the pattern of 4 and then 2. Then I highlight both of them, let go of the mouse, grab the magic fill button, and fill it down. And then I have to say, oh, but the last one only gets used once. So then here I can do it like before. I can get my sum, and then I'll take h over 3 this time times my sum. So a spreadsheet's a pretty handy way to do this. And h was again what? Pi over 8. Thank you. Oh, wrong spot. And then divided by 3 times my sum. So Simpsons Rule says the answer is more like 10. Trapezoidal Rule said the answer was 9.8-ish. The next thing we have to do is calculate the error for each of these. Trap. Yeah, it's a trap. Look out. All right. So the spreadsheet can be done pretty easily. I'm going to post this before I forget. Get shareable link. Advanced. Share with anybody. Let's see, where should I post it? Down here. What do we call it? Spreadsheets. Trapezoid. If anybody wants to play with it, you can. All right, back to our notes here. New page. All right. So the error for the trapezoidal rule in absolute value is going to be less than or equal to some maximum that we have to calculate times the length of our interval cubed divided by 12 times the number of intervals squared. And that's for trapezoids. So for ours, we have to take a look at our function, f of x, which is 15 times the cosine. Where did I put that? Yep. Cosine, I'm going to call it x for now, over parentheses twice. No, 2 plus the sine of x, all squared. And the m, I have to calculate the second derivative for this one, I think it is. Yep. And I need to find the max of the second derivative. Oh, my pen's out of control. Come here. Oh, ruh-roh. There it goes. Okay, so I have to come up with f prime, and then I have to come up with f double prime in order to come up with that value m there. And that's one thing we were asked to do here. So at this point, I would be whipping out something like GeoGebra or Wolfram Alpha to calculate that. So I'm trying to remember how to type multiple derivatives here. What if I do d squared? Is there a derivative calculator? Yeah. Oh. There's another of, so let's just see what happens here. If I do, for example, the sine of x, does it understand what I mean? It does. Excellent. Okay. Yeah, so this says find the second derivative, right? The derivative of the derivative. Remember using that notation back last term? Okay, so I had to do a d squared over dx squared, and then I can plug in whatever I want. So we have 15 times the cosine of x divided by parentheses 2 plus the sine of x, is that right? All squared. No, I think it's okay there. I'm squaring my denominator, which is that parenthesis and that one. No, I don't think so. I'm going to hit enter and see. Yeah, when in doubt, hit enter and it'll write it pretty. Yep, I got it correct. Whoa, look at that sucker right there. Okay. So you said there's a derivative calculator like the integral calculator? Oh, derivative calculator. By the same guys. Look at that. Oh, this is beautiful. All right, so we've got the sine, no. 15 times the cosine of x divided by parentheses. Oh, it doesn't like me doing that. Oh, fine. 2 plus the sine of x. And how do I tell it to find multiple? How many times? Oh, this is sweet. Go. Oh, that's. Oh, we missed the square. Okay, where does that go? Right there. All right, you guys have good eyes. All right, go. Thinking. Wow, this thing rocks. Where was this when I went to school? Okay, so it's saying that right there is the answer. So let's compare that. Oh, that was just the first derivative? Oh, second derivative. Oh, look at that. All right, let's compare this to, can I compare it to Wolfram? Is that my second right there? And then Wolfram said, oh gosh, I don't want to hear that. Oh, come on, move, would you? There we go. Just use them to double check. Yeah, okay. I just checked before I put in the answer. So they wrote it a wee bit different. Plus fourth cubed. Yeah, I'm sure with trig identities we can get those to match. I'm sure they're both right. All right. Anyway, they both show us pictures, which is nice. So let's see. We want the max on the interval from negative pi over 2 to pi over 2. So there's pi. So the max, yeah, well, oh, there's pi there. Pi over 2 is probably this asymptote. Yeah, it looks like it. That's not good. Because it's the it's the absolute value. So that means we want the highest or lowest number, which is a problem here, because this one drops forever toward pi over 2, it looks like. Plots. This one right here. It'll let me change the graph. Ooh, oh, nice. Oh, I can turn those off. Yeah, I'm pretty sure pi over 2 is going to be infinite. Pi over 2. Sorry, I don't like that. How about pi over 4? What? Interesting. How about, let's see, what's pi over 2 is about 0.7-ish, so negative 0.7. Okay. Negative 0.71. So it's going to keep dropping. Let me double check what is pi over. Oh, happy Pi Day, everybody. I forgot to say that. Let's see, pi over 2 is our endpoint. 1.57, what was I thinking? I was thinking pi over 4, okay. So 1.57, where did that go? Okay, there it is. So negative 1.57, I can't type today, 57. Yeah, that's putting me right at that asymptote. 0.56. Interesting. 0.55. Huh. I think this is wrong. 5.4. Is that number there? Oh, yeah, I could be wrong. I have to do some algebra. But we do have a bit of a problem. You with me on the problem? That max is like off the charts here. Oh, the third derivative will tell us what it is. Duh. I made a note of that in my last presentation online. Let's see. Oh, I guess I need that guy back, don't I? Calculate next higher derivative. Second derivative. All right, third derivative.
The result is too wide for the screen.
Okay, and so how do I want to do this? What if I type, it didn't like pi over 2, right? What if I type 1.57? Okay, so the third derivative isn't 0 there. So we are okay. I want to see just the third derivative. All right. So this must, okay, so there's my 1.57. Okay, so it looks like we do bottom out right over here, whatever that number is right there. That can't be right. Because I think it's telling me this yellow value is one. Let's see, 1 point. Where's 1.5? What is there? What are these numbers at the top? Oh, it's really, I see. We want to zoom in more. Yeah, so it's somewhere down here. No. Where's 0?
0 is to your left.
0. Oh, I want it to be negative. Okay. So maybe it is pi over 2, 0.7-ish. Yeah, so it's probably at pi over 4 is where we have our lowest value, which appears to be around 2. No, around 1.5. So let's go with that. All right, that was crazy. So second derivative evaluated at approximately pi over 4 is about, what would we say, 1.5-ish, 1.6-ish? Let's call it 1.6-ish. And then, oh, I can ask. Nah, that's good enough. All right, so calculating, so I think that's about what m is here. So 1.6 times my interval cubed. So my interval was pi over 2 to negative pi over 2, which is pi wide, over 12 times n was 8 squared. So this is about my error here. So let's calculate that. Let's see, we're doing the trapezoidal rule first. Error is going to be about, I'm thinking 1.6 times the interval pi cubed over 12 over, what was the other one, 8 squared? About 0.06-ish. What did the homework guide say? Number, oh, they claim it's about 0.2-ish. Huh. Am I looking at the right one? Number 5. The only thing, no, I typed it in right. I think the only thing I could have gotten wrong is m at 1.6. So, no, because it's the absolute value. M is the absolute value. Yeah, so it's always going to be positive. I'm just going to double check with Wolfram alpha. If I take the third derivative and set it equal to 0, it will give me critical points for the second derivative. Maybe. And is it going to give me it'll just give me approximation somewhere on here. Okay, here we go. Capital Z stands for integer. So where Z is any integer. So they give me general solutions to it. So it looks like 2 times pi times n minus this number right here is one way to look at it. Oh, there's multiple ones. Oh, come on, you're not helping me out. I want, if I click on one, will it tell me what it is? No. I thought Wolfram alpha would be more helpful. So let's see, we're going between, so we probably want one of these right here. What's that? Oh, there we go. Okay, so that one says 0.22-ish, and this one says negative 1.14. So let's try each of those. So 0.222, negative 1.14. Negative 1.14 gives me, ooh, check that out. It's about 26.9-ish, 27. What was the other one? Positive 0.222. That one's about 2. Okay, so for us, it's that other one, negative 1.14. So I way underestimated. So it's more like 27 instead of 1.6. Let's see, where'd that go? Oh, wow. That's quite a bit different too. Pi cubed. Let's try Simpsons Rule, see what we get. Simpsons Rule, we have to go even farther.
Why did you have 12
Good question. Back here, it should be, oh, did I not square it? It should be divided by 12. What's that? Yeah, so when you type into a calculator, if you wanted to do this right here, you could either type it as, say, the 1.6 times pi cubed. I'm dividing by 12 here, and I'm dividing by 8 squared. So that's exactly the same thing as saying 1.6 times pi cubed divided by parentheses 12 times, 12 times 8 squared. So these two are equal. Yeah, so I didn't feel like typing the parentheses. It was less ink. So let's see. Back here, our error, that was supposed to be an E, not a sum, for Simpsons Rule, an absolute value is going to be m times parentheses the width of the interval to the 5th power over, what's this one, 180 times n to the 4th power. So we have to come up with a guess on m. So let's do that. So I'm going to use both of those tools to help me do that. So if we want the fourth derivative, we need to figure out where the fourth derivative is extreme. So we need the fifth derivative to test that. So I'm gonna have to calculate the fifth derivative for this sucker and set it equal to 0. Can Wolfram Alpha do it? Oh my gosh, look at that thing.
That hurts me in a fundamental.
Okay. All right, so we want one of these guys here. So what's that one? Negative, better write this down, negative 1.27. That's in our boundaries. Or negative 0.52. Or negative 1.07. No, positive 1.07. All right, so let's go to that other calculator. Oops, where'd it go? There it is. And we want to calculate another derivative. First, second, third. This result was too wide for the screen. Let's turn those guys off. And we only want to know about, so let's see, we can kind of, oh, if I zoom in. Ooh. Yeah. Oh, well, I'm just going to type in some of those numbers. All right, so my numbers were negative 1.27. Fourth derivative is 333-ish. I don't know. We got to check the other ones. Negative 0.52. Negative 71. That's not extreme enough. 1.07. Okay, it looks like it is our 333-ish from the negative 1.27-ish. Oops, did I type something wrong? Oh yeah, there it is, yeah. So about 333.5-ish. Okay, so back to the drawing board. Where the heck's my drawing board? There it is. So we think M, and again, M is equal to the max of the absolute value of our fourth derivative on that interval from B to A, or A to B, sorry. So we think M is about 333. There we go. Our interval is pi wide, so we're gonna have pi to the fifth divided by 180 times the number of intervals, 8 to the fourth power. So this is our error, sorry, is not equal to, it's less than or equal to that. So spreadsheet, Simpsons Rule, error. Somebody double check, make sure I get this right. 333 times pi raised to the fifth, right? Divided by 180 divided by 8 raised to the fourth, right? Error here is about 0.138. Online homework says, what the hell? The error can't be negative.
Can't be negative. Means that you got so precise.
Interesting. Oh, no, the error can be negative, I lied. Usually we look at the absolute value of the error. And they got 0.02, interesting. Both their values are different than mine. I'll have to check that out some more. I don't believe there's, yeah, I'll have to go back and try that out. I will do that. All right, if you get a different M than theirs, feel free to hit that Ask Your Instructor button. And wow, that took all this time, holy shit. All right, happy Pi Day. So we will start section 7 tomorrow. One cool thing about section 7, isn't that right? That's what I said, isn't it? Yeah. One cool thing about section 7 is we're going to look at a figure called Gabriel's horn. Yeah, so consider the function 1 over x. And imagine revolving that around the x-axis. If we do that, we're going to generate a shape that looks like this. So can you see what that kind of looks like, a horn? Okay. So interesting thing is it possible for us to let this horn go on forever in this direction? Now what's going to happen? This is an asymptote, right? So this is going to get tighter and tighter and tighter as we go this way. So here's the question. What is the volume of Gabriel's horn? How much air or paint could it hold? And then how much paint would it take to cover Gabriel's horn in gold, for example, paint? It takes all of it. So we're going to compare the volume of Gabriel's horn to the surface area of Gabriel's horn. And Gabriel's horn is infinitely long. It goes on forever and ever and ever. Okay. Yeah. So improper integrals are any place where you try to integrate across a vertical asymptote, or you try to let one of the left or right boundaries go to the right or left forever, is what the next section's about. It's pretty cool stuff. All right. Have a good pi day. Feel free to help yourself some more pi on the way out. I'll catch you later, Gerald. Sorry I don't have pi for you there.
Oh, I don't